Welcome, everyone to iCap Academy.
Oh, I'm so excited for today, Sasha. We're diving deep into something truly foundational, aren't we?
Absolutely, Marina. Today, we're kicking off our iCap capstone project, and it's all about software architecture to vibe coding. It's a huge topic, but so critical.
Vibe coding. I love that. It already sounds much more intuitive than traditional approaches. So what exactly are we getting into today?
Today, we're dissecting the fundamental elements of software architecture. It's like setting the stage for everything we build, you know?
Okay, fundamental elements. That sounds like the bedrock. So Sasha, how do we even begin to define software architecture?
Great question, Marina. Think of it as the blueprint. Not just any blueprint, but the one for a massive, complex software system.
A blueprint. That makes so much sense. Like an architect sketching out a building before any construction starts.
Exactly. It's the high-level structure. It defines how all the different pieces interact, how responsibilities are divided up, and crucially, how the system is going to evolve over time.
Evolve over time. That's a key point, isn't it? Because software is never really done.
Never. It's a living, breathing thing. And a good architecture plans for that growth, for those changes. It's future-proofing, in a way.
Future-proofing, I like that. So when we talk about these pieces or components, what exactly are we referring to, Sasha?
Excellent segue. There are several key aspects here. First off, we have system components. These are the big players, the modules, the services, the layers that perform very specific tasks within your application.
System components. Okay, so like the individual engines in a car, each doing its specific job?
Precisely. Then, we have software components themselves. This is where we talk about the platforms you're building on, the frameworks you choose, the programming languages, and, of course, the databases.
Platforms, frameworks, languages, databases. That's a lot to consider. So how do all these different pieces talk to each other?
That's where connectors come in. They are the communication mechanisms. Think of APIs, for instance, or various protocols. They are the bridges between those components, making sure everything flows smoothly.
APIs, protocols. So like the roads and highways connecting different cities. Got it. What about the actual design choices, the how-to?
That brings us to patterns and styles. These describe the design approaches we use, like Model View Controller, MVC, or microservices, which is so popular now. Layered architectures, event-driven ones. They are proven ways to structure things.
The blueprints for the blueprints, in a way. Best practices that have stood the test of time.
Exactly. And finally, a really critical part, non-functional concerns. These are things like security, logging in, controlling access to functions and data, or maintainability.
Non-functional, but they sound super functional and important.
They are. They're absolutely critical for a system's health and longevity. Maintainability, for example, can be achieved with reusable components for security or workflow, and ensuring proper version management and release procedures.
So like, the building might look great, but if it's not secure or can't be repaired, it's not truly good.
Perfect analogy, Marina. Just like an architect's blueprint for a building doesn't show every single nail or wire, software architecture doesn't detail every line of code. But it guides the construction. And it ensures that long-term integrity of the whole structure.
Long-term integrity. That's the dream for any software project, isn't it? No tech debt nightmares down the line.
Precisely. Now, let's take all these abstract ideas and make them super concrete. Let's look at the architecture of a web-based application, starting with the system architecture.
Ooh, this is where it gets real. Show me the connection, Sasha.
This diagram illustrates the physical devices, the servers, the system software involved. On the left, we have the user device. That's your laptop, your tablet, your phone, where your browser is running, right?
My phone, checking the podcast. Yes?
That user device connects, via the internet, to a cloud data center. Inside that data center, you'll typically find an application server and a database server. These usually run on virtual private servers, VPS, or as platform as a service offerings.
VPS or PaaS. Okay, what's the difference there? That sounds important.
It is. Virtual private servers, or VPS, run as virtual machines on physical servers. They use virtual machine emulation software like VMware or Xen. Once you have access to a VPS, you can log in over the internet. You see files. You install software. You can do everything as if it were your very own machine. It's amazing control.
So a VPS is like renting a whole virtual computer. I can do anything I want with it.
Exactly. Examples of cloud services with VPS offerings are Google Cloud, DigitalOcean, Kamatera. They give you that raw power and flexibility.
And PaaS, platform as a service?
On the other hand, a platform as a service provider runs your application code in a secure environment. Rather than offering full control over a virtual machine, they abstract that away. You just deploy your code.
So less control, but maybe more convenience for deployment?
Precisely. Most commonly used web application frameworks like React or Flask are supported. Vercel and Google App Engine are great examples of PaaS providers. Some, like Anvil, even offer specialized development environments of their own, rather than supporting commonly used frameworks. We'll definitely touch on Anvil later.
Oh, that's intriguing. Specialized environments. And what about the databases themselves?
Databases like MySQL or Postgres. You can install them on your own VPS. Or, you can use platform as a service versions offered by the same or different cloud providers. It's all about choice and what suits your needs.
So I could have my application on one cloud and my database on another if I wanted to?
You absolutely could. The connections within the data center are often over a private network. But it can also be over a virtual private network running over the internet. Or, even the open internet, especially if different cloud platforms are involved for different application components or the database.
Wow, the complexity of these connections sounds like a real puzzle to solve.
It is. We'll see instances of these variations in the examples to follow. Now, let's move even deeper. Let's examine the software architecture of a web-based application. Focusing on the system's software, the languages, the frameworks.
Alright, so from the physical stuff to the code and logic, my favorite part.
Exactly. In this diagram, we see the browser. It sends HTTP requests to the web server. The web server, often built with languages like Python, Java, or C, processes these requests.
Okay, so my browser talks to the web server first.
Yes, but the browser also directly interacts with the application server via API requests. And it receives API responses directly from it.
Oh, so sometimes the browser bypasses the web server for certain things?
Precisely for the core application logic. The application server handles that. It's usually developed using Python frameworks like Flask, FasterPI, Anvil. Or JavaScript frameworks like Node.js with Express, or React.js.
So the application server is where all the brains of the app live. Fascinating.
Yep. The web server communicates with the application server using local inter-process communication services, if they're on the same virtual machine. If not, this communication might also be over the internet on HTTP. It's quite flexible.
So many ways for things to talk to each other.
And both the application server, and in some cases, the web server, communicate with the database. Using SQL or NoSQL queries. The application server sends database queries and updates.
Database queries. That's the data flow, right? Getting information in and out.
Indeed. Data can flow between the database and the application server. Or, even directly to the client in some instances, which we'll see later. And the browser itself runs the application's user interface. Built using HTML, CSS, JavaScript. And sometimes even Python, through specific frameworks like Anvil.
Python in the browser? That sounds like magic, Sasha.
It feels like magic. It's revolutionary in its own way. Now, let's look at a concise overview. This table provides a clear picture of different software architecture frameworks and their choices across client, page rendering and page logic, application server, and database.
A table. I love a good summary. So for the client side, what are the big options?
For the client, you have options like HTML and CSS with simple JavaScript. Or, a more complex JavaScript setup, of course. React is another super popular choice. And then there's Anvil Python. It's a niche framework where the user interface code can be written entirely in Python, yet it runs right in the browser. It's amazing.
That's incredible. Python in the browser. So what about how the pages actually get drawn and processed?
Page rendering and logic can be server-side and client-side combined. or purely client-side. Especially with frameworks like React or Anvil, which run much of the user interface logic entirely in the browser. They only access the server for data management or other API calls, like for AI services. We'll see examples of these soon.
So client-side rendering sounds like a very dynamic and interactive user experience.
It absolutely is. For the application server, Python choices include Flask, FasterPI, and Anvil uplink. For JavaScript, Node with Express is a very common solution. Server code created using any of these can be hosted using either VPS or platform as a service providers. It's quite flexible.
Choices everywhere. And databases, Sasha, SQL or NoSQL, right?
Exactly. The choice is typically between SQL or NoSQL. But there's an orthogonal choice, transactional versus non-transactional databases. Transaction support is needed for data management applications where concurrent access to the same data is common. Like banking systems.
Concurrent access. So many people trying to update the same thing at the same time.
Yes. However, transaction support comes with performance overheads. And it requires very careful programming to avoid deadlocks. Most web applications, surprisingly, manage with non-transactional databases. They handle concurrency using application logic, rather than relying on transaction support from the database.
That's a huge insight. So not every app needs that heavy transaction overhead.
No. And also, transaction support usually comes with SQL databases. It's often missing in NoSQL options. It's a big design decision.
Wow, so many layers to consider. Let's talk about some common frameworks then. Flask first?
Absolutely. Flask-based architectures are a very common setup for Python web development. Flask itself is a Python framework, and it can be used alongside other Python frameworks like FasterPI or Anvil. It's super versatile.
Flask, okay. So how does a Flask application typically work?
In a Flask-based application, the browser makes page requests to the web server, which often uses Gunnercon or Overcon as a WSGI server. The web server then passes the request, via local system calls using the CGI protocol, to the Flask application server. It's a very established flow.
So the request goes through a few steps before it hits the Flask app itself.
Yes, the Flask application server handles the core application logic, processing API requests and sending back API responses to the browser using REST. The Flask-based server code also interacts with the database, sending database queries and updates, using SQL or NoSQL operations. Common databases include MySQL and Postgres. A niche choice, but one we'll be using a lot, is Anvil.
Anvil again. It sounds like it's quite integrated into different parts of the ecosystem.
It truly is. HTML templates are served from the Flask web server to the browser. Thus, user interface logic, such as page flow, can be coded on the server, generating HTML pages dynamically and sending these back to the browser as needed. On the other hand, some user interface logic can be run in the browser using JavaScript. So, Flask offers the flexibility of a mix of server-side and client-side rendering of user interface logic. It's very adaptable.
That's a lot of flexibility. You can choose what part of the UI logic lives where. That's powerful.
It is. Now, let's explore React, JS-based architectures. These use client-side rendering exclusively. This is where things get super dynamic in the browser.
React. Everyone talks about React. So what's different about it?
In this setup, the browser runs in HTML, CSS, and JavaScript. And the entire user interface logic is in JavaScript. It's loaded initially into the browser. So, the React-based code in the browser makes API requests to the application server using REST.
So the React app lives mostly in the user's browser and just talks to the server for data.
Precisely. The application server, which can be built with Python frameworks like Flask or Anvil, or JavaScript frameworks like Express.js, processes these requests and sends back API responses to the browser. The application server also handles database queries and updates, interacting with databases like MySQL, Anvil, or Postgres, using SQL or NoSQL approaches. Often through REST, WebSockets, or sockets. The key difference here is the prominent role of JavaScript and React on the client side for dynamic user interfaces. It's really about that interactive experience.
That makes sense. It feels like the UI is very responsive then.
It absolutely is. The React framework allows for component-based development of HTML, CSS, and JavaScript logic. And it has facilitated the creation of a massive ecosystem of reusable user interface components, which accounts for its popularity today.
Reusable components. That sounds like a dream for developers, saving so much time.
It is a dream. For complex applications, a React-based user interface offers greater maintainability of user interface logic than, say, a Flask-based user interface using pure HTML, CSS, and JavaScript. At the same time, the learning curve for React is steeper. It's a trade-off.
A steeper learning curve but better maintainability for complex projects. That makes sense. And hosting?
The React application can be hosted on a platform as a service provider such as Vercel or Google Cloud. Note that the server application will also need to be hosted separately. As React is purely a user interface framework, the application server platform needs to be chosen and hosted independently. It's two distinct deployments.
So, two different hosting environments, one for the front end, one for the back end. Good to know. And finally, that niche one, Anvil.
Anvil. Let's consider this niche platform as a service framework. It offers a pure Python web development experience. It's truly unique.
Pure Python? This is where my Python love comes in.
Indeed. In this Anvil-based architecture, the browser directly runs Python code. It uses a Python interpreter written in JavaScript. It makes API requests using REST or Anvil's uplink WebSocket-based library, and receives responses from the application server, which itself runs Python. Perhaps on a platform like Vercel, or directly within Anvil's cloud. It's incredibly streamlined.
So the browser has Python running in it. That's just wild, Sasha, and it talks directly to the database?
It can. The browser can also directly communicate with the database, using NoSQL over Anvil uplink, which significantly simplifies the typical three-tier architecture. It's a big departure from traditional setups.
A two-tier kind of feel then? Less complexity in some ways?
Exactly. The web server, which is part of Anvil, handles the initial requests. And the database is often the Anvil-provided Postgres database. The application server also interacts with the database for NoSQL operations and can use Anvil's database library for communication. This setup highlights how niche frameworks can streamline and integrate multiple components. And get this, it's possible to mash up Flask-based, pure HTML and JavaScript, or even React-based applications within an integrating Anvil application. It's surprisingly versatile for integration.
Mashups. So Anvil can be a hub for different kinds of applications. That's incredibly powerful for building complex systems.
It really is. So, Marina, what have we covered so far? We've learned that software architecture describes a software system's components and their interactions. It's the grand plan.
Yes, the blueprint, and it specifies system components like devices, operating systems, system software, and network protocols.
Precisely. It also specifies client, server, and database platforms, the languages, the frameworks, and how page and data flow occurs. We've described the system and software components of web applications in quite a lot of detail, haven't we?
Yes, we've gone deep, from the user's device all the way to the database and back.
And we've touched on example choices for client, server, and database technologies. For the client, you might choose between HTML, CSS, and JavaScript, React, or that amazing pure Python UI framework like Anvil. So many options, right?
So many, but it's good to know the landscape. And for the server?
For the server, popular choices include Flask, Anvil, and FasterPI. And we've considered page flow, whether it's client-side versus server-side rendering. Each has its unique advantages.
Yes, balancing interactivity and performance. And databases?
For databases, options range from MySQL and Postgres to Anvil's integrated database. And whether to use SQL or NoSQL approaches. Plus, that important decision about transactional versus non-transactional needs.
It's like a giant puzzle with so many interconnected pieces, Sasha. And each choice has a ripple effect.
It truly does, Marina. This concludes our first lesson on the elements of software architecture. We've covered the core definitions, the components, And we've explored different architectures for web-based applications, including system and software layers. And specific frameworks like Anvil, Flask, and React.
What a foundational understanding. I feel like my brain is buzzing with possibilities.
This foundational understanding is crucial, Marina, as we move forward with our capstone project. Next, we shall explore different examples of software architecture, starting with a React-based architecture. And we'll use AI-based, vibe coding, using the Lovable platform to accelerate our journey. It's going to be so exciting.
AI-based vibe coding. I can't wait for that, Sasha.
As we shall experience, Marina, knowledge of software architecture is even more crucial while vibe coding in the new era of AI-accelerated development. Since AI writes most of the code, the human developer's contribution now needs to be much more on the architectural aspects. Starting with how different components talk to each other. It's a paradigm shift.
That's a powerful thought. So it's not about writing every line of code, but understanding the grand design, especially with AI. This is truly the future of being a software engineer in the age of artificial intelligence.
Absolutely, Marina. It's all about that high-level vision. Be sure to join us for the next lesson.
You won't want to miss it.